Okay, good. So we continue our discussion. On classical observable problems. So we have Laplacian of u equals to is, okay, and what we have found is that we have this class u in PR of m that is defined as in R of 0, the origin is a free boundary point, and d square u has these bounds. Okay. And what we found is that we can go close to a global solution provided we take R large. And not only that, we can respect the minimal diameter. But the limiting profile would also have the same minimal diameter. So now and the next thing that we looked at was that the global solution, and you know that when it goes to a global solution, for the global solution, this is still a free boundary point. You see why? Because of the non-degeneracy estimate. Yeah? Non-degeneracy estimate tells you that how there is a strict quadratic decay. So there will be a positive side and there will be a zero side. Okay. So now the thing is that what we know is that if U is a global solution, if U is in P infinity n, U is convex. And what we have done is that if the minimal diameter of the set intersection B1 is bigger than or equal to sigma, then there exists a order sigma by 2n ball inside. So I will call this rho. Okay. So now I want to know what can I say about this the free boundary of this global solution. Okay. Of course, it's a concave graph, right? Because the zero set is convex, so it's a concave graph. So qualitatively, it is Lipschitz, but I sort of want to get a more quantitative information depending on this rho. Okay, I want to sort of upgrade this information so that I can go back to my original solution. Because just knowing that it's a concave Lipschitz graph doesn't take me anywhere, because it does not translate into any sort of quantitative information for the free boundary of my original problem U, which is in PR of m. Okay. So now what do I do? So now with the convexity information, I will tell you that I can tell you that this is much better than just a concave Lipschitz graph, because I have an entire ball that is inside. So I will draw a big ball. Okay. I'll draw a big ball and I'll just pretend that. So I have so at a distance here, okay, I have suppose a very big ball, which is of order rho. Because then I want to show that, so this is of order rho. Then I want to show that at this origin or anywhere nearby, if I take a very small ball of order rho by 10 million, 20 million, 30 million, I don't know what to say, then, and if I take any ray from here that passes this ball, okay, then along this ray, the derivatives are monotone. So this is the set where U is bigger than 0, U naught is bigger than 0, so U naught is a global solution. So let's call it U naught, okay? Well, let's call U only, because I will write the derivative as UE, or let me write it as U naught, okay? So U naught is a global solution, which is the limiting profile of a blow-up sequence, which I don't know is unique, but I will tell that if the coincidence set is good, posteriori I will obtain that is unique. So how do I show this? So take any ray from here that passes this cone, okay? Now on this side, U is 0. So any directional derivative is 0, okay? And suppose, so the other thing that I assume is that the axis of this ball is say En, okay? Because the ball lies somewhere, I assume that the axis of the ball is En, okay? So En is the axis of the ball. And what I do now is that I take all rays that passes this cone, and I want to say that for all such rays, the directional derivative along that ray, along that direction, are all monotone. Why? Because here I have U is 0. So here on this, del E of U is equal to 0, right? Agreed? And here I hit a free boundary point. And here, if it turns out that del E of U is 0, that means that zeros have propagated here. Zeros are here also, right? And now the thing is, if I enlarge my ball even a little bit more, then here is a 0. I can cover it by other rays and fill these zeros. So therefore, and likewise, if I enlarge it here, then I can cover this with zeros, because this ball lies in the zero set. I can also cover this with zeros. So once I know that along this line it's a zero, because the zero set is convex, so along all of these lines, it has to be throughout zero. And this will tell me that there is a full neighborhood around zero, where u is zero, so it cannot be a free boundary point. So if I know along one line, if I go far away from towards the boundary of this ball, then I can fill this volume. And if I go below, I can fill the other volume. So therefore, it tells me that if I take a narrow enough ray compared to the size of the radius, I will always have a strict monotonicity across this. Okay? So this is the proof. Okay? That's all, nothing else. Okay? But I don't know how he thought about it. That is a different story. Okay, so let me quantify this statement. U naught is in P infinity M, and let me sort of write this as some En. Okay? That P of rho of En along this is inside the coincidence set. Then there exists a cone of monotonicity. Okay, there is a cone of monotonicity 0 depending on rho, because the number of such things that you can do will depend on rho, right? Yeah, it depends on the size of this ball. So there exists a cone of monotonicity, which is the set of all E such that E minus En is less than delta, and this delta depends on rho. Means it cannot be for too many directions. Like if I take a very wide direction, I will escape this ball. And then it doesn't say anything, because outside this ball, my zero set can end. I only have a good luxury of sort of taking my rays so that they enter this ball. If it goes outside the ball, I am dead. Okay? So therefore, I need to be not that greedy. I just need to take this narrow cone. So therefore, there is a delta rho such that LE of U, okay, U naught, is strictly bigger than 0 in the set in B of, say, rho by 10 million, okay? B by rho, I have to decide a constant, B rho by n of 0 intersect the positivity set. Right? That is exactly what this is telling. As soon as I escape this, the directional derivatives have to be strictly bigger than 0. Because if it is 0, it is a convex function, right? It has to be 0 on the entire line, and therefore the whole zeros will spread, because I'm starting from the 0 that is inside. Okay? And not only this will happen for all cones if I tilt the cone a bit. So instead of taking En with axis, if I tilt the cone a bit, if this ball is very big, and if I'm willing to compromise more, I can put myself in a narrower cone. So therefore, and not only that, if I move the cones little bit and I center the ball, it would still be the same, right? Because these rays will not be that different, right? So if I take a size rho around this on the free boundary, I would still be able to cover it with all these rays that start from this gigantic ball that I've drawn over here. So what I find is the following. So if I take any cone of directions at any free boundary point over here, there is a uniform cone of monotonicity, not just at 0, but this will happen. So not only that, happens for all x in B by 10 million of 0 intersect gamma. I just need to compromise a bit. And then what happens? What happens is that at every point, if you leave the cone, U becomes positive. If you leave the cone, U is positive. Likewise, there is a cone of monotonicity below, which is inside the 0 set for the same reason. Because there cannot be a non-zero inside, right? So there is a cone, the same cone that is inside the 0 set, and there is the same cone outside the 0 set of a fixed angle, and that angle with the cone of monotonicity is decided by the size of this ball. So therefore, at every free boundary point in this small place, I can find at every free boundary point I can find a cone from above and cone from below. And so therefore, it just tells me that this free boundary is quantitatively Lipschitz in a way which is decided by this rho parameter. So let me just write this down. So under this hypothesis, so I will call it under the hypothesis star with no mention of lemma, under star, under the fact that star is valid, I have that the free boundary there. So there exists a large constant in naught such that the rho of 0 intersection b n naught such that b rho by n naught intersection the free boundary is a Lipschitz graph. Because at every free boundary point, I can find a cone of a fixed angle. So therefore, the graph, the free boundary is trapped between these cones at every point in a uniform way. And not only that, okay, and not only that, in this Lipschitz graph, I have more information. I have that information that in a cone of directions, the directional derivative strictly increases in the positivity set. And not only that, moreover, what I have is that there exists some 0 around En such that for all E in 0 of En, okay, cone dependent on En, you have that del E of U naught is strictly bigger than 0 in the set the rho by whatever this number is, rho by n naught of 0 intersection the positivity set. Okay, and now not only can I find a cone of monotonicity around En, I can find a cone of monotonicity if I tilt my En a bit. Okay, because if the Ens don't tilt too much, this ball is good enough to consume for me all my rays. Right? This is the engulfing property of a cone. Because if I have a cone along a certain direction, okay, if I have a fat enough cone in a certain direction, if I narrow my cone, I can fill it, I can put my axis somewhere else, which is strictly inside. But I can do it in a way with a fixed ratio of the angle of the outer cone divided by the inner cone, okay? And that is only decided by the size of this ball that I have. Okay, good. So I have that not only it can be represented as a Lipschitz graph in Xn, it can be represented as a Lipschitz graph with respect to every such direction. So this will tell me that, so because I have a cone around En, so if I just follow En, I can only hit this free boundary at one point. I cannot hit it at multiple points. But since I can tilt my cone a bit, I can write it as a graph so that is like the, you see, like with respect to the change coordinates, okay? So, okay, this is good enough for me. So this is like my another Cn times rho. So let me write it as little Cn times rho, okay? Because this is entirely dimensional. If this rho is there, this is entirely dimensional, okay? Little Cn times rho, which is still positive. Question? No, I'm just tilting the cone a bit. So if here I have monotonicity, and then if I take the axis little bit here and take this cone, I can engulf it in this bigger cone. Yes, but if I take an axis here, I'm still contained in this bigger cone with axis that makes sense. So I know that in this fat cone, there is monotonicity. But then if I take the axis somewhere here, I can still find this cone. Makes sense? But I can tilt it with a fixed angle so that the ratio of this angle divided by the bigger angle is kind of the same, comparable to 1. When I say comparable to 1 means bounded below. Okay. So this is there, great information for me. But now, how do I go back to my original problem? Okay. So now here is what I do. I need to sort of make it more cohesive. So what I do is the following. Here is my free boundary under that assumption, And here is something, and suppose I take any E in this narrower cone, C tilde of rho, means I make my cone even possibly narrower, so that I can tilt it at any angle. Okay. So around this, there is a cone of monotonicity. Agree? Clear? So now, so now here is what I do. I take some point over here. Okay, at a distance, at a certain distance. Okay, that I will say it later. At a distance d. Now, if you remember my non-degeneracy estimate, I need not have taken my ball over here. I could have moved my ball here, and if I again constructed the same sort of quadratic function, I would be able to get the same conclusion. Make sense? So I need not center my ball here. I could have centered my ball at any other point. Means I could have centered my ball at any point that intersects the boundary. Right? Because I started with a point y which is away from the center, then I moved this y back to this free boundary point. So I could have done it. So if I take it here, because now I have more qualitative information, in my earlier picture, this could have been wild, that I would not have a cone. But now since I have a cone, then I know that there is a good chunk of the positivity set, right? Where there is. So here in this cone, if I find a ball and say this is the direction E, okay? Clear? Then what do I know? So along this, there exists at least one point where what happens? Where U is like D square. There is at least one point here where U is like D square, right? And so then if I sort of join this point, then what I would have is the following. So if I join this point to this point, what do I get? So suppose this point is somewhere over here, which is at say UDE. Okay. So U of DE minus U of 0 or any point wherever. Okay, it need not be 0. I move it to my new 0. Okay. Where this will be of the order. This will be of the order D square. Okay. And this is less than or equal to max of UE, means del E of U in this whole line, right? In this whole line, till it touches the point where the maximum is attained, okay? Multiplied with D. Agreed? The max of this. I'm just majorizing this. So then I can cut this D. So at least I would know one point where this directional derivative is at least D. Because otherwise, if the directional derivative, this is simple, because if the directional derivative is less than D, too much less than D, I can never produce to you a uniform non-degeneracy estimate if I use fundamental theorem of calculus along one line. And now, so I know one point on this cone where del E of U is at least D. But I know another information now. I know that del E of U is positive in this cone. So by Harnack, del E of D, U is comparable to D in this whole ball, because this ball is away from the boundary by a distance D. Distance comparable to D, because inside D, I can find this little ball of size D by something which is decided by the angle of this cone, right? So everywhere here, my del E of U naught is exactly D. Not exactly D, but comparable to D. And what can you say about U? U is like D square. So if D is very small, then I know the following. So if D is very small, I know that del E of U naught minus U naught is strictly bigger than 0. Agree? Or if you want, you put a constant. Okay? Or not constant here, but constant here. Because for large enough, if D is larger than 1, that is where you need to adjust this constant, or D is comparable to 1. For small enough D will dominate over D square. Okay? So therefore, just to sort of fix it in all range, you just put a constant up front. Okay? So del E of D is bigger than or equal to 0. So not only I got that this is bigger than or equal to 0, in this cone I also get that constant del E of U naught minus U naught is bigger than 0 in this entire region. In this entire B rho by 10 of this set. Okay? And now this is enough for me to come back. Now note that I know that if I have the following. So what did I show in the first lemma? That given, recall. Now I approach my local solutions. That given epsilon bigger than 0 and sigma bigger than 0, there exists R sigma such that if for the local solutions, the minimal diameter of U such that for R bigger than equal to R sigma, if U is in PR of M, if if del of U equals to 0 intersection T1 crosses the sigma, then I can find U naught global convex such that U minus U naught in C1 norm is less than in B1 is less than equal to epsilon. Right? So therefore, if I apply it over here, this happens in BCN. So this happens in BCN row of 0 intersection gamma of U naught, positivity set of U naught. And this happens for all E's in C row of 0, C row of En. Okay?
That happens when a point is comparable, which is far enough from the boundary, let's say D. But you are saying that happens near the point.
No, but it is far enough from the boundary proportional to D. Why? Because the thing is that I have a cone.
Yeah.
So along this cone, I know that the distance is D. If I have to escape this cone, I have already escaped D. There is no way that I can hit the boundary without crossing the cone at this angle. But if I have a triangle, if this is some length and if this is a good angle, then this length and this length are all the same. So they are almost equilateral.
Okay.
It is far from equilateral, but it's just a line joke. Okay. But whatever it is, my whole point is that we ignore all constants if you have to do this theory. Okay.
A small chunk, right?
Yes, it's a small chunk, but it's a comparable chunk compared to and this chunk. The epsilon d ball that you can get inside only depends on the angle of this cone, nothing else.
But you're saying this happens everywhere near the 0, right? On a small level.
Yes. Because you take any point here,
Okay.
and then you can always find the nearest point,
Okay.
and then you can find this nearest cone,
Okay.
and then you can find this ball. Got it? Yeah, I agree. There is a lot of details, but this is what I'm trying to condense a 10 lecture into 3-4 lectures. It's a very good point. So this is there. So now if I have to sort of fight back to this problem, what do I get? If I know that this gets approximated in B1, so it gets approximated here as well, right? So therefore, what I would know is that in this case, I will get that the original one, if del E of U minus U will be bigger than equal to minus epsilon in B Cn rho. See, this does not just happen. So this monotonicity bigger than equal to 0 also happens away from the positivity set, because on the 0 set they are both 0. Okay, so I can just replace this information over here. It is the non-triviality is only in the positivity set, but now I replace it by the whole ball, because I would not know except for the 0 how the interface changes from one solution to the other solution. But then I don't care, because now I can sort of just take it over the entire ball. Good. So this is what you have. Now you seem to be in a little bit of a trouble, because you have not been able to achieve the monotonicity that you need. Because now for the original U that you would approximate, del E of U is not quite positive. So you cannot make a cone for the original U, right? So whatever you do, you see, like this is because even if the solution, so this is just a reflection of the fact that if a sequence of functions converges in even a C infinity norm to another function, the interfaces are highly unstable, right? So that is why the whole theory of nodal sets and everything is so hard. There is no relationship between the 0 set of a solution and the coefficients. So it is not like the Schroeder theory. So you can have thin interfaces which in the limit becomes fat. But now here you have an additional information that allows you to gain a bit. You haven't gained a monotonicity, but you have gained something close. Okay? So this is also another point where you would think that you are almost dead. After doing all this work, when you come back to this original problem, you still haven't achieved what you expected to. And this is where comes Caffarelli's another beautiful lemma, which is the jump lemma. I really don't know. I mean, how he thought about all of this. When I give you the proof, it's so simple. But then I don't know how the idea is. So that says that, so here is my U, okay? Here is my U, and here is this 0, and here is this ball, okay, of 0. Okay. Now I say that, so now the claim is that if this epsilon that I have over there is very small compared to this rho, Cn rho, so let's call it by a certain name. Let's call it, say, another sigma. Who cares, right? If this is less, because rho came from sigma, so this is like another. So if epsilon is very small compared to the sigma, then you have that del u of u is bigger than or equal to 0 in b sigma by 2. You see, like there could be negativity here, little bit of negativity, but if epsilon is very close, then in half the ball, I can improve my positivity. So Caffarelli calls it the jump lemma, and this will be a salient feature even in the thin obstacle problem that I will do tomorrow, where it could be equally competitive or equally demanding. So how do I prove it? There is this idea. You take del E of u, okay? And so what you do is that you take any point in half the set. Let's take this point x naught, okay? You take any point in half the set, and now you cook up a quadratic polynomial. You remember, like we had already done a non-degeneracy estimate, and now we just want to do it again, okay? So what you do is that, well, it is different from that in the sense that you will see how it is different. So del E of u minus u, okay? That is why you need to retain this minus u. This is your friend now, because in the non-degeneracy it was u minus that, but now here is a minus u, and so therefore to make this harmonic in a way so that it is positive on the boundary, I have a good freedom to add a good chunk of x minus x naught squared over 2n with a little alpha. Okay. Now what can you say about this h? This h is harmonic. Okay. This h is bigger than or equal to 0 on the free boundary, because both this and this are 0 on the free boundary, and this is positive on the free boundary. And if I go far enough over here, this thing is at most minus epsilon, but if this thing is like comparable to sigma square. So therefore, if the sigma is very large compared to this epsilon, I would have that this harmonic function is also positive on this boundary. So then by maximum principle, h of x naught has to be bigger than or equal to 0, and that is just telling you that del E of u of x naught minus u of x naught is bigger than or equal to 0. And this happens for every point x naught which is away from the sigma boundary. And now I can forget this because u is bigger than or equal to 0. So therefore, in half the set, in b sigma by 2, I have that del E of u is bigger than or equal to 0. Okay? And now, so therefore, what does it tell you for my u in PRM? So I know that. So this is my claim. So if so given sigma, there exists R sigma. Now I can forget the epsilon. Epsilon has been adjusted in the sigma. Okay. There exists R sigma such that if R is bigger than or equal to R sigma and U is in PRM, or it automatically means origin is a free boundary point, and P1 is bigger than or equal to sigma. This implies that B little sigma n, this Cn is another Cn, okay, in intersection gamma is Lipschitz. And not only that, del E of u is bigger than or equal to 0, just say with respect to xn, which I can fix, right? Because I can rotate, and Laplacian is kind of invariant with rotation. Such that for all E in some cone delta around En. So I have shown that if I have a good coincidence set, then the free boundary is Lipschitz. Okay? And now I want to upgrade this to not only Lipschitz, I want to say more. I will now upgrade this to C1 alpha. So I change the lemma in a flash. How do I do it? Well, this is where my first lecture comes into play, which is boundary harmony. So now I know that the free boundary that I have is a Lipschitz graph, xn equals to f of x prime. And if I use the interface equation, u of x prime f of x prime equals to 0, it gives me that if I have to write any angular derivative, u of xi for I between 1 and n is simply equals to minus uxn times f of xi. Or said differently, f of xi equals to minus uxi by uxn. So if I know that this ratio is C alpha, then I'm done. But this ratio is kind of harmonic outside. But I cannot apply the boundary harmonic to this right away because I don't know whether u of xi is positive, right? I just have a Lipschitz graph. Okay? But then I exploit the fact that not only there is one direction where it's monotone, it happens in a cone of direction. So this is how I just sort of fix this in a very minute way. This is not a big deal. I'm kind of not doing bad with the regular set, but we'll see how far I go. So other than all of you, Shrikant is also watching me very closely. I'm just joking. So then the thing is that what you do is that given any EI, where say, okay, you know that delta EI plus EN is inside the C delta cone, right? And now I can apply, instead of U, I can take E to be this. So then I would know that U of E by U of N is C alpha. Because both are non-negative, harmonic function vanishes on the free boundary, which is Lipschitz, then this is C alpha. But now I expand it. If I expand this, this is the same as telling delta UE by UN plus UN over UN is C alpha. This I can ignore because this is 1. So this just tells me that UE over UN, so sorry, not UE, UXI. UEI, XI. You understand what I mean, right? It's a partial with respect to U. EI by UN is C alpha. And so therefore my graph is C alpha. The derivative of the graph is C alpha. This is C1 alpha. And then you can bootstrap to C infinity. So the conventional method uses the holograph transform, which is about, it goes to the intrinsic coordinates and sort of flattens the boundary. Okay. And then you sort of get a fully nonlinear PD even for the Laplacian. And then you sort of improve using the boundary regularity theory that has been developed by Agman, Douglas, and Nirenberg in the well-known paper back in the late 1950s. But the thing is that now there is a more elegant approach to doing that, and it gives you in one stroke C infinity. And that is an approach due to De Silva and Sabine. Beautiful approach due to De Silva and Sabine in 2014 based on higher order boundary Harnack. So if you use the higher order boundary Harnack, it gives you C infinity in one flash, provided you don't go into the proof. Okay. So what does it say? So it says that if U and V are two, I mean, you don't require one to be non-negative. So I'll just state it for non-negative because so Laplacian V equals to 0 without any non-negativity, and Laplacian of U, because once you have C1 alpha, you have much better control over everything. Okay, and Laplacian U is equals to 0, and U is non-negative, and both U and V are 0 on this part of the boundary. And suppose this domain is Ck alpha for any k, for given k in 1 to infinity. Okay, then what Sabine and De Silva show is that V by U is in Ck alpha. Now, if U is non-negative, U is 0, then U is like V by U is like the normal derivative of U, right? So if you apply the Schroeder theory, if you think of V by U, this is like the normal derivative of U, normal derivative, let's call it U mu, right? Because by the Hopf lemma, if U is non-zero, U is normalized somewhere, you have to be sort of pointing in the direction of the normal, right? In the inside, in the direction of inward normal. Now, what does the Schroeder theory tell? The Schroeder theory tells you that if the domain is Ck alpha, then the solution is Ck alpha. That would just tell you that the Neumann derivative is Ck minus 1 alpha. So what Sabine and De Silva do is that they show that if you divide it by not just the, if you don't take the Neumann derivative, or if you just don't divide it by another Ck alpha function, but by divided by a solution to an equation which is harmonic, then you get one better than what you can get from the Schroeder theory. So I'm just trying to say that they don't prove something that is covered by the classical theory. They get something which is incredibly insightful and imaginative. So for some of you who know well, this is another He's a very well-known mathematician. I mean, if you are doing fully nonlinear PDs, you will see his and free boundary problem. You will see this name all across, and he's one student of Luis Caffarelli. Okay.
So what was the exact result? So B.
Okay. No. So I have not told the proof. I got too much engrossed into serving.
No, I'm saying what is the exact statement of?
So the B by Luis CK alpha up to the boundary. Or CK alpha up to the boundary. Okay, that is the important. And now, how do I apply it? So how do I apply it? Now I know that it is C1 alpha, right? So now that I know that the free boundary is C1 alpha, then I apply to del xi u. Now I don't need the sign over del x and u. These are harmonic here. 0 on this free boundary because the function vanishes up to the first derivative. That is, it doesn't make an angle with the coincidence set. Then this ratio now in the C1 alpha domain is not just C alpha that the boundary Harnack gave. It is one better. It is C1 alpha. And if I now go here, I get that this is C1 alpha. So this is C2 alpha. And then C2 alpha again. If I go back and forth, I keep bootstrapping and get all the way up to C infinity. So this is where the theory stops. And now I want to tell you that how do I go back to my original problem? Okay, so now let me just write it down because at this point there is not much to do, but still it's good to write down. Okay, so now my lemma is the following. If U is in P1M, so there exists a modulus of continuity. What do I denote? Eta R, monoton, eta of 0 plus equals to 0, such that if for some R naught, you have that the minimal diameter U equals to 0 intersection BR, but since you are scaling, when you want to scale it to B1, you have to divide by R, right? You see, like when you do QRX, you have to take this. So this you call as the rescale minimal diameter is bigger than equal to eta of R naught. This implies that gamma, gamma of U intersection B Cn sigma R naught R naught is C infinity. This sigma R naught comes because of that minimal diameter thing. Okay, so eta R. So let me call this sigma R naught only because this sigma relates to that sigma. Okay, sigma diameter. Okay, so B sigma R naught is a. So that tells you in particular that all. So these are typically the regular points where the coincidence set has positive density. Okay, the non-degeneracy estimate tells you that the zero set, the positivity set has to have a good density, right? That is what the non-degeneracy estimate tells you. So therefore, in order to get something better, I would need to assume that the coincidence set has zero positive density because there are examples by Sheffer where you can have these kind of free boundary points. Here, the coincidence set has zero density, and you see that there is a spike. So you don't get any regularity. And in fact, I told you that the Sheffer example of Sheffer is quite deep because it gives you Laplacian equals to 1 on this set. But if you don't care about it, I'm sure that my examples would work. This is one part I don't want Luis Caffarelli to ever hit here, but I'm quite sure that if you take U to be square, you see, like you cannot get Laplacian U equals to 1 times the characteristic function of the set where U is bigger than 0, but you can get some F, which is F is a very nice set. In the sense that what you do is that all these problems you approximate it in a way and try to apply the Cauchy-Kovalevsky theorem to smooth approximating problems that are going to this closed set. And I'm very sure that you can do it. You can build it up for arbitrary Cantor-like closed sets as well. So the coincidence set can be very bad. So these are kind of bad forms. But on this part, okay. So now how do I show this? So this is essentially done. Okay. I just need to go from UR to that U capital R. So there I have that. For every sigma, there is this R sigma. So sigma going to R sigma can be chosen in a monoton increasing manner, right? And when I take U R of x to be U of Rx over R square, then this R is like 1 by R. So this I can write it as 1 by R sigma. Right? Agreed? So therefore, what I can say is the following, that sigma. So, is it clear? So this is like 1 by R sigma. So to say that if if U is in T1M, then U of R sigma, okay, which is defined as U of R sigma dot divided by R sigma naught square. This is in T1 by R sigma, which is R sigma. Okay. So therefore, I have that this sigma to this R sigma can also be chosen to be in a monotone, strictly monotone way, right? And then what I do is that I define this sigma R as the inverse of this mapping. So you define this one as the inverse of this mapping, and that is how you get this modulus of continuity sigma R. So as soon as you cross this sigma R naught, because what does it mean? This simply means that if I take U of R sigma R naught, then for this I will have that U of R sigma R naught equals to 0 intersection B1 is bigger than or equal to sigma R naught. And this is U of R sigma R naught is in P of 1 by R sigma R naught, which is P of R sigma R naught. And that is how sigma R and R sigma and R sigma are selected, right? So therefore, it tells me that if I zoom in enough, and if the rescale, is it clear that this R will sort of be taken care of? This should be R naught. This R will be taken care of by that. Okay? Yeah? So therefore, if I zoom in enough, and if at some level I find that the coincidence set has good density, which is quantitatively expressed in terms of the minimum diameter, then I would have that in a smaller enough set. This is a C infinity graph. So this is just telling you that these are the regular free boundary points. So these are the free boundary points where the zero set has positive density. So now posteriori, once you know that it is C infinity, and here you have Laplacian equals to 1, so you will know that here you have a good Taylor expansion. So what will be the limiting profile? You understand, right? Here is Laplacian equals to, and here gamma is C infinity. So let me just write it down in a better way. So now I will tell that posteriori at such points, the blow-up limits are half-space solutions, right? Earlier they could be anything arbitrary, which I didn't know, but now I know posteriori, after proving the regularity, that they have to be half-space solutions. So assume that the tangent plane is 0. So here Laplacian equals to 1, right? So because the tangent plane is xn equals to 0, I will have that all the uxi's are 0 over here, right? Clear? And now, so the thing is that you have to respect that Laplacian equals to 1. This essentially tells you that the limiting profile for this would be 1 by 2 xn plus whole square. And there are no other possibilities, right? Yeah. So I mean, in the sense that you will also get u of xn, xi's are all 0, right? Because u of xn is 0 here, and uxn is harmonic, and uxn is 0 on this free boundary. So all the tangential derivatives are 0 here. So u of xn, xi is 0. So the only thing that survives is u of xn, u of xnn. And but because it has to respect this Laplacian equals to 1, it doesn't have a choice except to be this. So the Taylor expansion on this side will be u will be equal to half of xn squared plus higher order term. So when you quadratically rescale, you get a half plane solution because this is the region of the coincidence set. I mean, it need not be sort of convex. Okay, I'm just trying to tell you. I mean, it could be like in some other directions. It could be coming in.
I mean, to do that, C2 is good enough. Why do you need C infinity?
I get C infinity, so I just have the luxury.
Oh, but
it's not a major point.
C2 is good enough, right?
But so the major point was just to say that the blow-up limits in this case are half-plane solutions. So that is only the.
As soon as we have a tangent, we can do that. Right?
So therefore, on the hind side, not only I have, it cannot go. So that if one sequence goes to one blow-up limit, the whole sequence has to go to the same blow-up limit. That is something that you obtain posteriori once you know the regularity of the free boundary. So now let's try to understand the complement of this point. So I seem to be doing good. Okay, so now I have sort of finished my understanding of the regular part. So this is what Caffarelli did in his sort of famous ACTA paper, and that he revisited in 1980 in his CPD paper, Compactness Methods in Free Boundary Problems. The ACTA paper is, I don't even know, I mean, I find it very hard to sort of follow. But the CPD paper is essentially the same results, but it's more like clearing out some bushes and seeing the forest more. So there has been sort of multiple attempts and revisits on Caffarelli's stuff, okay, by Caffarelli himself and few of his collaborators. But these are kind of very legendary papers that have been written on this subject. And if you see the Abel Prize citation, the first thing it says, he came into scene with the boundaries, right? And this is the famous ACTA paper result. But it leaves out points. What it leaves out is that, so this is one regular point, right? So x naught in the free boundary of U is regular if for all r bigger than 0, the diameter of the set where U is equal to 0 intersect BR, where R is bigger than equal to sigma of R. Where this sigma of R is this modulus of continuity. So what is the complement? So then it's a regular point. So the singular point is of U is the gamma of U minus regular points. So if x naught is a singular point of U, it means that intersection BR goes to 0. So goes to 0 as R goes to 0, right? And so in the sense that it is less than equal to sigma R, which goes to 0 as R goes to 0. That is the important thing. It means that when I look at BR intersect the coincidence set, at least there will be some axis where it is trapped by not just R, but sigma R times R. At least along some axis, it is trapped by sigma R times R. So therefore, what you have is that at such singular points, U equals to 0 intersection BR is less than equal to sigma R along some direction, and all other directions, which is like R to the n minus 1. So they add up to R to the n. So these are precisely points of 0 density. So these are precisely points where the coincidence set has 0 density, right? So, and regular points posteriorly we obtain are precisely the points which are of positive density. First, we classify everything in terms of minimal diameter, but once you prove the regularity of the regular set, you posteriorly get that you can have this alternate classification that regular points are positive density points of the coincidence set, singular points are the opposite ones. But these singular points can be very bad, very wide. The whole free boundary can be composed of singular points. Instead of taking the 1 by 2 xn square, I can just 1 by 2 xn plus square, I can simply take 1 by 2 xn square, then the whole x prime equals to xn equals to 0 are singular points, because on both sides U is positive, right? So the whole free boundary can be composed. Of course, here the singular set is very smooth. So it can be smooth, but it can be very wide too. As I said with these examples, so these are places where I can have arbitrary sort of small links. And Sheffer already has these kind of examples. And in fact, it can be even wider than that. So I can have a ball, right? So I'm just drawing my coincidence set. I can have a line, right? This is the line of singular points. And then I can have a plane of singular points. And then I have, say, a regular point. So these are all the points where these are my coincidence points, okay? And it need not be that it needs to fill the whole line. It could be very fractal like inside. And then I can have a few discrete points. So what I'm trying to say is that the singular points can have different dimensions depending on the polynomial that is over there, okay? So there could be a line of vanishing, there could be a plane of vanishing, there could be a point of vanishing. But before I even get to that, the other main problem is that even though this is less than equal to this, what does it mean? Let's try to quantify it further. So this is something that, so now there is a certain problem that is there in the singular point. What is it? That every time the axis of the minimal diameter can rotate. So along some arc, you can have that the singular set is trapped in this direction, where this is the axis, the ER. So the singular set is trapped in all this direction. So this will be the set of all in BR, inside BR. The singular set is trapped inside here. So that means that this will be the set of all E So suppose 0 is the point, 0 is the singular point. Set of all E says that E dot ER is less than sigma R, right? So this is what which will trap this, right? So let me see. So this is the plane. This is between two planes, and ER is the normal. So this would be E dot ER would be less than equal to sigma R, right? So that is, it makes a very it makes an angle which is close to 90 degrees with this, and along this it is sigma R. So it is trapped in this kind of a set. But in the next scale R2, this the singular set can be trapped in a plane with different axes, right? Trapped between two planes in a different axis. So these planes can rotate, and the axis of the plane, in some sense, if you see, is dictated by the axis of the plane is dictated by what is the quadratic approximation at the singular point, right? Where is the difficulty? The difficulty is that along any subsequence, it will go to a quadratic polynomial that I will show, but this quadratic polynomial can change across a different sequence. So therefore, the zeros can kind of rotate in a very convoluted manner, and at least from the current understanding, there is no guarantee that you can have a good stratification result of the singular set. If I have a picture like this, even if it is pentol-like, at least I can say that it is contained in a line. But if this is too wide, that it rotates too much, then I cannot contain it in any one-dimensional C1 manifold, because then that whole manifold has to be like a coil as well, and that is not good, right? So the zero set across different scales should not rotate too much, right? The singular points cannot rotate too much, and that is the same as showing that the blow-up limit at a singular point is unique. So first I want to sort of get some results, and then I will try to use Harish's AC Alt-Caffarelli Friedman monotonicity formula to say that there is a unique quadratic polynomial that goes to. Okay. All right. So not bad. It's clear, right? That these planes can rotate. A priori, there is no guarantee. And the other thing about singular points, unfortunately, is that you cannot play it around the same way as you do with a regular point. Because, for instance, if you have something like this, right, obstacle, and if you lower this a bit, lower this even a little bit, then this point, which was a singular point, if you lower this a bit, this cannot go below 0, right? Because it is bigger than equal to 0, and this simply becomes a singular point becomes a regular point. So in this, after this small epsilon perturbation, I get a new picture. So all these compactness arguments that I did with regular points would not even apply to the singular points. What I'm trying to say. So if I lower this a bit, then it cannot cross the 0. So by this small perturbation, it has to match at 0, right? At this epsilon, there is a small radius, right? Because it separates it quadratically, because there is no angle. And so when it lowers it, this cannot go below 0. So all these values would become 0. So this point, which was earlier a singular point, has now become a regular point. So you see, so even if you have good information about the limit along a certain subsequence, you cannot go back and apply it here, because a small epsilon perturbation can make a singular point regular. That doesn't happen over here because I have more information about this cone of monotonicity. Okay, so singular points are hard to analyze, but if they exist, they have to be studied. In fact, the whole free boundary can be composed, singular set can be quite large. So to this, Caffarelli didn't have an answer at that point, but until around 1998, where he found that an Alt-Caffarelli Friedman monotonicity formula that he found for some other problem can be applied to this problem, and that will give you that uniqueness of the blobs at the singular points. So before I go to that, let me establish a preliminary lemma before we get started. So whatever I'm saying, you expect that because the coincidence set becomes 0 along any sequence, it should go to a quadratic polynomial, right? Which is positive because it has to be convex. If 0 is there, it's convex, so it has to be above 0, right? That is the supporting hyperplane. So this is what I proved, that if U is in T1M, U is a singular point, then along any subsequence UR goes to some U0, which is a quadratic polynomial, and it goes to in C1 alpha way to a quadratic polynomial which is A of x comma x. A is bigger than equal to 0 and trace of A equals to 1. And why does that happen? So this happens because if I take any rj going to 0, and then if I take urj of x to be u of rjx divided by rj squared, then this is defined in p1 by rj of m, right? Then, because it's a singular point, I know that the minimal diameter of urj intersection 0 intersection rho intersection b rho over rho for any rho goes to 0, right? For any rho bigger than 0. Why? Because if I rescale back, this is nothing but sigma of rho rj less than equal to sigma of rho rj, because that is the classification of a singular point, right? By scaling back and forth. Because when I go back to b rho, that radius becomes rj rho, right? Clear? So therefore, URJs go to a global solution, do not, which is in P infinity n. So this doesn't distinguish between regular singular points because I could do it along any free boundary point, which in particular is 0, which is now assumed to be a singular point. Then what can I say about this U0? I would know that since this 0 set in B rho goes to 0, so for any RJ, there is a very small set, very tiny set, where URJs are 0, and outside that Laplacian of URJ equals to 1. And this set decreases in measure as RJ goes to 0, right? So therefore, by standard weak type arguments, I would say that URJ goes to U0 in this set. You will have that Laplacian of U0 equals to 1 almost everywhere in B rho. And this happens for every rho. Because this set, so this exceptional set, has measure going to 0. So any weak type argument will give that. And now this happens for every rho. So I will have that Laplacian of U0 equals to 1 almost everywhere. But almost everywhere or everywhere for this kind of an operator is a kind of the same, right? And therefore, by Liouville's theorem, and you have quadratic growth at infinity, because URJs have quadratic growth at infinity, so that also translates to that of for U, because U is P naught M, right? Because d square of U0 is less than or equal to M. So the Liouville theorem tells you that U0 has to be exactly of this form. The U0 has to be a quadratic polynomial. Okay. So now what? So now the same way that I found this modulus of continuity, I can put a modulus of continuity for the singular points, right? Except that this QRJs can change from scale to scale, which is to say that there exists a lemma U is in P1M and 0 is a singular point. Then there exists a modulus of continuity, let's call it eta r, okay? Such that for every r, you have that there exists QR, which is this polynomial. The same way, I go from local to global by this zooming in, okay? And then again, I get that for every epsilon, there exists a capital R epsilon for which that happens, right? And therefore, when I take capital R epsilon to be 1 by little r epsilon, I can go back and forth. And then I invert that mapping. That epsilon going to little r epsilon, if I invert the mapping, I get this eta of r. Clear? So this eta of r is obtained by a compactness argument, so it is very implicit. There is no good control, okay? But that is not the main problem. The main problem is that for every r there exists a QR. Such that what you have is that such a QR says that QR minus QR, that is the rescaling at this, or when I scale back, UR minus QR in B1, in C1 B1 is less than or equal to eta R. So if I scale back to U, I get that. So this is the same as having U minus grad QR over, so let me put QR here, grad QR over L infinity BR is less than equal to eta R, because this is how the gradient scale 1 survives, right? Because if I were to do this in C1, so this would simply be grad UR by R minus grad QR by R. This in this set, this will be less than equal to eta R, means if I move this R there, this is R eta R. And not only that, for the L infinity norm, you have that U minus QR over VR, VR is less than equal to eta R square. And this happens at every singular point. Now the main problem is that these polynomials can rotate. And how do you stop it? Okay, so then you have this monotonicity formula that tells you that what is the what Caffarelli used is this one Caffarelli-Friedman monotonicity formula that Harish said. It says that if you have two subharmonic functions, okay, U plus U minus bigger than equal to 0, such that they have disjoint support. And then if you look at this all Caffarelli-Friedman functional, which is phi of R, U plus, U minus, which is mod x to the power n minus 2. This is monotone. Okay. But this is not the way that I typically do it in my lectures. I do it by using a more simplified Monod's monotonicity formula, which is an anti-derivative of Weiss. Weiss is like a quantified Almgren, which is used in unique continuation problems a lot. So they are all related by one identity that people in the semilinear community also use a lot, which is the Relic-Posev identity. They're all related. Okay. However, the starting point was that somebody like Caffarelli in 1998 was able to identify that if you find the monotone functional, then you can capture how disordered this U will be at small scales. So in 1998, he used the all Caffarelli-Friedman to get the uniqueness of the blow-ups at singular points. So what is the monotonicity formula? So monotonicity formula is like an entropy formula, which says that at larger and larger scales, the function is very dramatic, but at smaller and smaller scales, it reorganizes into a linear function or a quadratic function and so on and so forth, right? Provided it satisfies some constraints. So this is what you have here. And now how do you apply it? So I will tell you that this was in 1998. Later on, Mono simplified it in 2003 by a different monotonicity formula by showing that U of 1 minus n plus 3 PR of U minus P square is monotone for all P such that all P quadratic polynomial which are in that class. That is all P which is equal to 1 by 2 AX X A bigger than equal to 0 trace A equals to 1. This quantity is monotone. So, but I will try to stick to this older all Caffarelli-Friedman one, okay, just to demonstrate how it works. And now, how do you think of this? Harish has told you several things that it's a very deep monotonicity formula, which is connected to the Friedland-Heyman inequality, which is about an information of the characteristic constant on complementary parts of the sphere. Now, how do you think of this inequality even further? Just think of the two-dimensional case where this n minus 2 is not there. This is just telling you that phi of r, which is equal to 1 by r square, 1 by r square, grad u square, suppose u is harmonic, grad u 1 square, and then it's another harmonic function, grad u 2 square, 1 by r square over dr is monotone. Right? This is what it says. So suppose there is this origin, right? And u1 is, say, a harmonic function over here, positive harmonic function, and u2 is somewhere over here. If you extend each of this by 0, they become subharmonic, right, across. So now the thing is that, what is this average? Tangentially, these are 0, right? So in the limit, so therefore, if phi r is monotone, it means that phi 0 plus is bounded. So this simply implies that phi of 0 plus is bounded, right? It is bounded by phi of 1. So that means that what is phi of 0 plus for this? This will be simply from this side the Neumann derivative of u mu plus square. This will be simply for this the Neumann derivative of u2 mu square. And this is telling you that u1 mu square times u2 mu square is bounded. And if you think of this u1 and u2 as the Green's function with a pole somewhere, okay, somewhere over here, right, somewhere inside, then this is just telling you that the kernel of the harmonic measure, okay, so if you have a domain on either side, the harmonic product of the harmonic measure is balanced. Because this is the kernel of the harmonic measure on this side, this is the kernel of the harmonic measure on this side, so the product is balanced. So if the harmonic measure is, so said differently, again I will go to my spike picture. If the harmonic measure is very good on one side, that if I take a Brownian motion, I can hit here very lightly. But then from this side, if I start the Brownian motion at a similar point, I will have very chance to hit this. So in a way, the product will be balanced. I mean, this is just easy to say that this is probably the inspiration, but how he sort of got into it was.
Why is that uniform on the point to see? Why is it uniform?
Well, it is at a point. I'm not trying to sort of quantify it too much. Okay, so you can quantify it, but that is not the point. But the main thing is to say that the product of these kernels are bounded. So in particular, if you remove this guy, they are bounded. But these are like the product of the harmonic measure, right? Because many of the Dirichlet problem representation, it is simply equal to minus del G by del mu of the boundary value. Remember? So this is like a, so this thing with the Hn minus 1 measure is like the harmonic measure. So this just tells you that the product of, so if I have one boundary which is boundary for both sides, then the product of the harmonic measure is kind of balanced in a good way. So this was done to understand different kinds of free boundary problems that he studied, which are the two-phase problems. That is where he applied this monotonicity formula. And one phase free boundary problem Harish is going to describe in his last lecture. There also he will prove that flat free boundaries are Lipschitz. So I'm just trying to say that Caffarelli was largely inspired by a similar phenomenon for minimal surfaces. So that was his inspiration. Okay. So, and that is indeed a very beautiful theory. So I think to have some good success of free boundary problems, I mean, one has to have some understanding of how this overall scheme and minimal surface theory is. So, and in some of these parallels also apply to this obstacle problem. That is a big part of it, right? But also the Bernoulli type problems came much later. So how do I apply it? Let me sort of just give you a good idea. Okay. So I applied it on two things. I applied on, so I take phi of, I applied on UE plus and UE minus when U is a solution. Okay. So then what I do is that I do it. So I apply it this way. I look at phi of R del E of U, which is just del E of U plus and del E of U minus. This is nothing but phi of R, the Alt-Caffarelli-Friedman functional, R del E of U plus, del E of U minus. Okay, and this is just a shorthand. I mean, this is how you sort of denote it, just for the simplicity. Okay, and now there is this feature, right? So you have this nice property, phi of R, the scaling property. The phi of R del E of U R, phi of R del E of U equals to phi of 1 del E of this rescale 1. Okay, and now I know that. So and now I know the following, right? So the rescale 1 del E of U R converges to some, suppose along a certain subsequence, it converges to some Q1. One of these quadratic polynomials, right? Which are convex quadratic polynomials such that Laplacian of Q equals to 1. Then I know that the set where URJ, the exceptional set, goes to 0. This will have small measure. But away from this set, in any ball, URJ and Q1 are C2 closed. Because both solve Laplacian of URJ and Laplacian of Q equals to 1. And these sets go to 0. So if I take the difference, so along a subsequence, phi of say RJ, phi of 1 LE URJ, okay, minus phi of 1 del E of Q, okay. So this will involve the integral, right? The integrals will have these exceptional sets which are going to 0. So you take this, and these exceptional sets in these integrals involved in the all Caffarelli-Friedman functional will have very small chunk. So this could be like, so what you do is that if this chunk is like sigma r, you take a strip to be sigma r to the 1/3. And so that this eta r is going to dominate over this sigma r. Make sense? Because outside this, I can apply the C2 estimates for harmonic functions to u minus q. Because outside this, I know that u minus q is like less than equal to sigma of r squared. So therefore, d square u minus d square q is less than equal to sigma r. But then there is a decay which is given by the distance, and this distance is like sigma r, say, to 1/3, right? Let me take something which is cube root of that, and then when I cut it, this is sigma r to the 2/3. That is still remaining. Okay. So because these points can be very, so I'm just assuming that this is my 0 set. I'm enlarging it by sigma 1/3 because sigma is much smaller than sigma 1/3. My zeros are trapped in sigma. I'm just taking a slightly bigger one because I just need some closeness. If sigma is a modulus of continuity, sigma 1/3 also is. And then I know if I take any point here, it will at least take sigma 1/3 time to reach here. Agreed? And these are the exceptional points of this. Of course, there is some clear way of doing it. I understand that I'm not giving all the details in the sense that it's only 10 minutes I want to wrap up, but this should be sufficiently convincing. On this part, so this will have something, the q's will have something, so that will have very small measure, and outside that, these integrals have closeness. These are integrable, right? Which is at r equals to 1. And why am I bothered? Because I need to know the second derivative, because the all Caffarelli-Friedman functional involves the second derivative, which in the whole ball only has Lipschitz C11 control. But I need to say that now I need to use the information that this is a singular point. So the exceptional set where the C11 control cannot be improved is a very small set, which is of the size which is sigma r. So I take the larger of the two modulus of continuity. Okay, I take the larger modulus of continuity, and then what I can say is that on the difference, because this minus this at the level of second derivatives are close except on a set of very small measure. So I can say that phi of 1 of del E of urj minus phi of 1 of del E of q, if r is small enough, is less than or equal to sigma rj. Where this sigma is some other sigma which is 1/3 of the previous sigma. And I do not want to quantify my sigma. I mean, now I think some of you like Harsh who would have attended my other course would know that the mono was much simpler, which is why mono came later in 2003. But I think still one has to give a lot of credit to Luis Caffarelli, right? I mean, even to think that to use this monotone continuity in this kind of problems, I don't think prior to this existed. So I mean, you see, one cannot take any credit of Caffarelli. To even think that one has to do something like this. Later on, you can improve upon your functional. That is a different thing. But I understand it's very messy, but it is what it is. Okay. So once you have this, then you are done. Why? Because if it happens along a subsequence, it goes to this cube. It has to happen across any other subsequence. So if along any other subsequence, because this quantity is monotone, because this quantity is nothing but phi of rj del E of u by the rescaling properties, and this has a limit. So if if this goes to this along any subsequence, it has to go to the same limit. So if I have two others, if I have another one q2, then I would make that phi of 1 of del E of q2 in the limit has to be equal to phi 1 of del E of q1. That is it. Along another sequence, we have another limit. And as soon as you have that, if you sort of evaluate it back, this quantity is nothing but q2 of E squared up to a dimensional constant. And this quantity is, well, sorry, when q2 is equal to 1/2 a2 xx, this is equal to a2 of x. Because when you take two derivatives, that disappears, and then you can take it out, a2 of E outside in the directional derivative. So this simply becomes what? This is so when you apply this functional to del E of q, where q is the structure, q is say half a of xx, this is nothing but a of E. So this becomes, and this is like roughly, because it's a positive definite matrix, it is like a of E square, right? This is a of E square. A1 of E square will be equal to A2 of E square for all. Right? But A1 and A2 are corresponding to Q1 and Q2 matrices. But this is, since this equality holds along all, therefore these two matrices have to be the same. So the blow up is unique. And now I am in business because now I just need to sort of put this information again together. But this is what is happening. Now I want to use the other thing. So what is this blow up? What is this D square? What is this A? If A is the matrix, then if A of x by x 1 by 2 is the blow up at 0, this just tells you that D square of U of 0 is like A. Right? This is the blow up at a singular point. Now I need to show that these blow ups are continuous across the singular points. And this is not very hard to show. Why? Because of the following. So suppose I have 2 points, x and y. Okay, which are singular points. So here I know, and suppose this distance is like r. So in 2r radius, because this is a universal modulus of continuity, what I suppose here the blow up is qx, here the blow up is qy. Here I will know that in this larger 3r ball, u minus qx in the larger b3r of y, 3r of x has to be less than equal to eta 3r, right? Eta 3r times r square, right? Agreed? Likewise, over here you will have that u minus in the same ball because it contains r ball of y or 5r ball of y. You will have that on the same set. U minus qy is less than over the same kind of thing is less than equal to eta 3r of r square. So that q of y. So that means that q x and qr y are this much close in eta 3r r square. So if I scale it to b1, right, in a br size ball, in a size of ball br, these two polynomials, quadratic polynomials, are in a ball size r is eta 3r r square close. So if I rescale, quadratically rescale in a b1 size ball centered somewhere, this is like eta 3r close, and this is the distance between x and y. And now I use the fact that all norms on finite dimensional spaces are equivalent, and the top order part, the quadratic part of both of this will be d square u of x at the singular point and d square of u of y at this singular point. So assuming that, this is all under the assumption that this is in sigma u, this is in sigma u. So therefore, these blow-ups, these second derivatives are kind of continuous across the singular point. This is another information. And now I'm in business. Caffarelli doesn't even write anything after this. He says that then you have the stratification. So morally, the argument is this. Morally, the singular set, suppose 0 is a singular point. So near 0, the singular set is like du equals to 0. Right? And now what you do is that given x in sigma, you send this to du of x. Okay? Call this mapping some f, right? It's Rn to Rn. Then what is the Jacobian of this mapping? Is d square u. Right? So therefore, by the implicit function theorem, and this sigma is contained in a Ck manifold, where k is the kernel of d square of u at whichever point. Okay? So I have to define sigma k is the set of all points x in sigma such that the kernel of qx, which is the blow up, is k. So therefore, sigma k is contained in C1 manifold of dimension k. And of course, this is not justified because what do I mean across this? But this can be justified by what analysts use Whitney extension. Because these are Taylor approximations of order 2, right? Better than 2, right? Because there is this modulus of continuity. Therefore, I can use Whitney extension to have a big F for which these polynomials are the Taylor expansion, because all the compatibility conditions in the Whitney extension are satisfied. So this formal argument of sending this to this is justified by a capital F, which is the Whitney extension of this du. Make sense? So this tells me that the singular points are contained in C1 manifold of dimension, which is decided by the kernel of this polynomial. So this is, I think, all that I have to say about the classical obstacle problem. Almost all ideas are there. And I can tell you for sure that whatever I list over there, this constraint, any serious analyst can do. Okay, so that does not require the minds of Luis Caffarelli. So at least this is a minimally expected thing that try to convince yourself, because I mean, one has to start somewhere, right? So this is all for now. Tomorrow will be another problem of a similar flavor, which is the thin obstacle problem, where the obstacle will be on a portion of the boundary, which is where Luis Caffarelli also made a lot of advances in the in around 2006 or 7, okay, and 10 and so, and that led to the lot of works that happened subsequently because of its connection to fractional obstacle problems. But this is all that I have to say, and I think Shrikant, we are done for today.